We are continuing our journey through evaluating limits, and this section is about a special theorem called the Squeeze Theorem, and helps us to evaluate what a limit would be. If we may not be able to find the limit of that particular function, but we can find the limit of a function that's smaller than it and that's bigger than it, and if they go to the same place, then we know that the one that we're talking about is going to go to that place. So that's the idea behind the Squeeze Theorem. So learning outcomes, evaluate the limit of a function by using the Squeeze Theorem. And let's see here. The idea is talking about, you got, here's your g of x is your function in question. H of x is always bigger. F of x is always smaller. And so if we come to a place that h of x and f of x are coming to the same limit, that means g of x would be going to that same limit. So our squeeze theorem is essentially f of x is less than or equal to g of x, less than or equal to h of x. If the limit as x approaches a of f of x is L, and so the limit of h of x as x approaches a is also L, that means that the limit for g of x as x approaches a would also be L. So let's start off here with the limit as x approaches 0 of x cosine of x. So this one's not so bad. Just realize that cosine of x is always going to be between 1 and -1. So if we extend that and multiply everything by x, we'd have negative x is less than or equal to x cosine of x less than or equal to x. And so if we look at the limit for each of these, the limit as x approaches 0 of negative x, well, that's going to be 0. And the limit as x approaches 0 of x is also going to be 0. Therefore, since we had that x cosine of x always falls between negative x and positive x, the limit as x approaches 0 of x cosine of x would also be 0. Let's try another one like that. Very, very similar problem here. We have this limit as x approaches 0 of x squared sine of 1 over x. So once again, if we said that -1 is less than or equal to sine of 1 over x, which is less than or equal to 1, we know that to be the case because the biggest sine can produce a 1, the smallest sine can produce -1, just like cosine. Now if we multiply everything by x squared, we'd have negative x squared is less than or equal to sine of 1 over x less than or equal to x squared. So if we look at the limit as x approaches 0 of negative x squared, that's going to be 0. And the limit as x approaches 0 of x squared is also going to be 0. Then we have our therefore. The limit as x approaches 0 of x squared sine of 1 over x must also be 0. Okay, moving on here. There's a video you can watch about this. We now use the squeeze theorem to tackle several very important limits. Although this discussion is somewhat lengthy, these limits provide invaluable and prove invaluable for the development of the material in both the next section and the next module. The first of these limits is limit as theta approaches 0 of sine of theta. So consider the unit circle. I'm going to scroll down here. You can see that. The figure we see that sine of theta is the y-coordinate on the unit circle, and it corresponds to the line segment shown in blue. The radian measure of angle theta is the length of the arc it subtends on the unit circle. So 0 is less than theta less than pi over 2, and 0 is less than sine of theta, which is less than theta. Okay, so we're going to come down here. So we're talking about the length of this line is defined by being sine of theta. So the limit of 0 as theta approaches 0 from the positive side is 0, and the limit of theta as theta approaches 0 from the positive side is 0. So by the squeeze theorem, the limit of sine of theta as theta approaches 0 from the positive side is 0. Makes a lot of sense to me. So let's look at the limit as theta approaches 0 from the left side of sine of theta. We're going to see that's also going to be 0. So that, I mean, we're going to conclude that the limit as theta approaches 0 from both sides then is of sine theta is 0. So this is uses the same type of thing. From negative pi over 2 is less than theta less than 0. And if you multiply everything by negative, you get 0 is less than negative theta less than pi over 2. So 0 is less than sine of negative theta less than negative theta. And the negative comes through on the sine. And so we have, by the squeeze theorem, we're looking at both sides of that. That limit for 0 is going to be 0, for theta is going to be 0, then for sine is 0. Sine is also 0, so that's our limit. Okay, moving on. So now we're going to look at another one. We have this relationship that you remember from your pre-calculus days, your trig days. Cosine of theta is the square root of 1 minus sine squared theta. For negative pi over 2 is less than theta less than pi over 2. So our limit is theta approaches 0 of cosine theta would be the same. The limit is that which is 1. Now we look at a limit that plays an important role later in the later modules, namely that the limit as theta approaches 0 of sine of theta over theta. This is a big deal here. To evaluate this limit, we use the unit circle in the figure 7 here. Notice that this figure adds one additional triangle to figure 8. We see the length of the side opposite the angle theta, and this new triangle is tangent theta. Thus, we see that 0 is less than theta less than pi over 2. So we're just talking about this quadrant. And in that, sine theta is less than theta less than tangent theta. Okay. So divided by sine theta, and all parts of the inequality we obtain. So dividing that by sine theta, we're going to get 1. We're going to get theta over sine. We're going to get tangent theta divided by sine. What are we going to get here? 1 is less than theta over sine theta, which is less than 1 over cosine. And then if you flip all the sides, you have 1's greater than sine theta over theta greater than cosine theta. So in this case, if we take our limit for each of these outside parts, limit of 1 as theta approaches 0 from the right side is 1, and the limit of cosine theta as theta approaches 0 from the right side is 1. Therefore, the limit of sine theta over theta as theta approaches 0 from the right side is 1. So by applying a manipulation similar to that used in the earlier part, we see the limit of sine theta is, as theta approaches 0 from the left side is 0. We can show then that the limit of sine theta over theta as theta approaches 0 from the left side is 1. So the big conclusion here that we want to take from this is we can use this now, that the limit of theta as theta approaches 0 of sine theta over theta is 1. So we're going to use this to establish that then also the limit of 1 minus cosine theta over 0 as theta approaches 0 is 0. So that gives us another thing here. So we're going to look at this and say, okay, let's multiply this by 1 plus cosine of theta over 1 plus cosine of theta. That gives us the limit as theta approaches 0 of 1 squared minus cosine squared theta all over theta times 1 plus cosine of theta. So that's going to be, that's 1 minus cosine squared theta, so it's, I forgot my limit. limit as theta approaches 0 of sine squared theta over theta times 1 plus cosine of theta. Now that sine squared, we could split that up and call that a limit as theta approaches 0, sine theta over the theta down below times sine theta over 1 plus cosine theta. Well, this first part, that's just going to equal 1. So it's really the second part that we're after. So we end up with a 1 times sine of theta is 0, 1 plus cosine of theta, well, cosine of 0 is 1. 1 plus 1 is, that's just that sine of 0 is 0. 1 plus cosine of 0 is 1 plus 1, which is 2. So this is just 0. So this gives us the conclusion that the limit of 1 minus cosine theta over theta as theta approaches 0 is 0. Okay. And I think there's a video you can watch if you want. Let's try another one of these. So in this case here, it's a similar process. We're going to multiply this by 1 plus cosine of theta over 1 plus cosine of theta. So we have the limit as theta approaches 0 of 1 minus cosine squared theta over sine of theta times 1 plus cosine of theta. Limit as theta approaches 0 of, that's a sine squared of theta, because 1 minus cosine squared theta is sine squared theta, over sine theta times 1 plus cosine of theta. So if you want to split that up, I don't know that it's really necessary to go to all this length of work, but we'll just do it. Theta approaches 0 of sine theta over sine theta times sine theta over 1 plus cosine of theta. So these sine thetas divide out. Or you can take the limit then too, because you get a 0. So what do we get? Sine of 0 is going to be 0. Cosine of 0 is 1, so it's 1 plus 1, so it's 0 over 2, which is 0. Looks like I think we have one more to look at. Okay, it says if 8 minus 9x squared is less than f of x, which is less than 8 times cosine of x, it says find f of x using the squeeze theorem. So for this, I would take the limit of 8 minus 9x squared as x approaches 0. So plugging that in, you just have 8 minus 0, which is 8. Also the limit as x approaches 0 of 8 cosine of x is going to be 8 times 1, which is 8. So since both directions, both sides of it go to 8, we conclude that the limit of f of x must be an 8. Okay, there's one last fun little exercise if you want to go through it. Talks about getting the area of a circle using the limits, and they go through here and look at this. Take a look at that. That's not going to be anything we're going to test on, so I thought that's just interesting to see. Okay, thank you.